Introductory Chemistry, Chapter 5, Molecules and Compounds. So there's two types of ways that we're going to talk about how atoms can bond. And so chemical bond occurs when two atoms either share their electrons or transfer their electrons. Joseph Proust discovered the law of constant composition, which says that for any given compound, you are going to have a fixed ratio of atoms for that particular compound. So it's a fixed ratio of atoms and it's a fixed ratio of mass. So for example, if we have, which most likely is hydrogen, and oxygen, we know that hydrogen and oxygen can come together to form water. So this says that for every water molecule, there will be one oxygen atom for every two hydrogen atoms. If we look at the mass, we know that hydrogen weighs approximately 1 AMU, and oxygen weighs 16. So if you have two hydrogen atoms, that would be a mass of 2 AMUs. And comparing 16 to 2, then in water, we have a fixed ratio of mass of oxygen to hydrogen that is 8 to 1. So every water molecule will have this composition. So the two types of compounds or bonds that we're going to talk about are ionic bonds and covalent bonds. Ionic bonds occur when one atom gives up electrons and another atom will accept electrons. So metal atoms give up their electrons, nonmetals accept those electrons. Then we become positively and negatively charged respectively and form a bond based on the attractive forces that occur between opposite charges. In a covalent bond, we look at two nonmetals or a semimetal and a nonmetal coming together and sharing their electrons. So some bonds actually have characteristics of both types and are not easily identified as one or the other. So sometimes it's a sliding scale of how much have we really shared our electrons? Is one atom actually holding on to those electrons a little more closely to itself than its partner atom that it's bonded with? So different ways to represent a particular compound. So our first and broadest definition would be the chemical formula, which simply tells you the number and the type of atoms that are present. The empirical formula is going to be your simplest whole number ratio of atoms for a given compound. Your molecular formula represents the true formula for that compound. So here we have ammonia, carbon tetrachloride, hydrogen peroxide, water, and elemental hydrogen. And I would like to state here that all of these are molecular formulas, and they're all empirical formulas except for H2O2, which means we could simplify that by dividing both of these by 2 and see that then it would be H1O1. A structural formula is going to tell you the connectivity between the atoms. So it still tells you how many atoms there are and what type of atom, but it gives you more detail because then it shows you which atoms are bonded to each other for a particular compound. A formula unit is used to represent an ionic compound. Because in ionic compounds, you have repeating patterns of cations surrounded by anions, surrounded by cations, etc. We look at the basic, what are the two atoms that came together? What are their charges? So here we have ionic compounds that are representing a formula unit, whereas when we talk about a molecular formula, we're talking about nonmetals all bonded together. And molecular formulas are discrete compounds, they're discrete molecular units, so there is no repeating pattern. We can use molecular modeling kits to actually put together atoms and see how they are bonded in a 3D representation. So here we're showing the difference between a formula unit of an ionic compound versus a molecule. We see here this repeating pattern of sodium ions and chloride ions, but we know that the ionic compound is based off of neutralizing those charges, 1 sodium for every 1 chlorine, and then they just repeat. So it's part of this more extensive crystal lattice structure. Whereas a formula unit for a molecule, we're just sharing a set amount of electrons. So there is no repeating pattern. This is a molecule of methane, and it's a CH4. So each one of these is its own little unit. So in ionic bonding, we have ions of opposite charge that are being held together through electrostatic forces. This occurs because one atom would like to give up its electrons to become more stable, and the other atom would like to accept those electrons to become more stable. And this is generally happening between a metal and a nonmetal. So down here we see that sodium starts with 11 protons, it starts with 11 electrons, it gives up one electron to become more stable. As it does that, it shrinks. So now sodium has 10 electrons. Chlorine starts with 17 protons, 17 electrons. It's going to accept that electron. It's going to increase in size and end up with 18 electrons. Then, because we have something that's positive and something that's negative, they come together and form this crystal lattice structure. Keep in mind that when we do any type of chemical reaction, we are not changing the number of protons for a given atom. So here's some common monoatomic cations and anions. And we've talked about this in class about looking at group numbers and how can we associate those with charges. So we know that metals like to give up electrons. And if you're a main group element, you're going to follow your group number. If I'm a group 1 metal, I become +1. If I'm a group 2 metal, I become +2. If I'm a group 3 metal, I become +3. Then we start to get into nonmetals. Well, carbon kind of has its own branch of chemistry, but it's a nonmetal, so it's going to become negative. So it's going to be -4. And then nitrogen's group is 5. So we go 5 minus 8 to get -3, 6 minus 8 to get -2, 7 minus 8 to get -1. Why are we looking at the noble gases? Because these atoms are going to accept electrons so it can have a similar number of electrons as what its nearest noble gas neighbor will. Stability is the name of the game. So then we also have some transition metals listed down here. Keeping in mind that chromium through nickel, they typically take a +2 or a +3. We've got 5 elements in a row. 2 + 3 is 5. In your group 1Bs, each of these, copper, silver, and gold, all take a +1, and then copper is a +2 and gold becomes a +3. In our group 2B, we have everything taking a +2 charge, and then mercury is special because it actually forms a diatomic cation, and that's the mercury 1 ion. And then when we look at tin and lead, even though they're not a transition metal, they are big enough that they can vary the amount of electrons that they give up. So these are metals in group 4, so they are a +4. They are also 2 places away from the transition metals, and they are a +2. So we can use our periodic table to determine certain charges. So how do we write formulas for ionic compounds? Well, the first thing you need to know is what is the charge on each of those. Metals are going to become positive, nonmetals are going to become negative. We just looked at the periodic table and how to determine some of those specific charges. When you figure out what your chemical formula is, you have to have a net charge of 0. So that means you need all of the positive charge to cancel out all of the negative charge. So we use what's called the crisscross method. Over here and looking at what happens between aluminum and oxygen, aluminum's a group 3 metal, so it's +3. Oxygen is a group 6 nonmetal, so it is a -2. If we pull the charges down without the signs, we don't include positives and negatives, then we see that it's Al2O3, which means that you need 2 aluminums at a +3 charge, so 2 times 3 is 6. And you need 3 oxygen atoms at a -2 charge. 3 times -2 is -6. So 6 minus 6 is 0. The crisscross method will always work. So how can we predict some formulas for the ionic compounds formed from these ions, these pairs of elements? Sodium and oxygen. Sodium is a +1, oxygen is a -2. We crisscross those down and end up with Na2O. Lithium is a +1, bromine is a -1, We crisscross those, we end up with LiBr. We just looked at aluminum and oxygen. Aluminum is a +3, oxygen is a -2. Crisscross those, Al2O3. Barium is a group 2 metal, it is +2. Fluorine is a group 7 nonmetal, it is -1. So we crisscross those and end up with BaF2. So we just have to look at the charges, we put them up there, we pull them down, we make the numbers of the charges become subscripts, and we ignore the signs on them. So once we've written a particular formula, how do we name it? How do we name our compounds? Because we have to be able to communicate what things mean in chemistry. So we always name the cation first because it shows up first. So it always goes metal and then nonmetals, just like in the alphabet, M comes before N. So cation is just the cation, we name it. The anion, we change the ending to IDE. These are for what we call type 1 binary compounds. Binary meaning that there's only 2 different elements present, not the number of those atoms that might be there, but there's only 2. So here we have 1 metal, 1 nonmetal, 1 metal, 1 nonmetal, 1 metal, 1 nonmetal, etc. The cation is our metal, so we just look at what this is and we say it. We name what the metal is. Then we look at the nonmetal and change the ending to IDE. So sodium chloride, sodium oxide, lithium sulfide, aluminum bromide, and calcium oxide. So that is how we name things when we have a main group metal, meaning it's not going to take a different charge. It's always one specific charge. So we saw with that periodic table how transition metals can have 2 different charges. So how do we indicate which charge that particular metal is for a compound? Well, what I like to call the old school method is you had to know the Latin name for those particular metals. Iron is ferrum, so we would represent the higher charge with an ic ending and the lower charge with an us ending, ferric or ferrous. Silver would be argentic. Oh no, silver, sorry, take that back. Silver is only 1 charge, but the Latin name for silver is argentum. Lead is plumbum, so you'd have plumbic or plumbus. Gold is aurum, you'd have auric or auris, etc. Who wants to know Latin? Probably not. So we have a new school method which says we're going to state the name of the metal and simply include in parentheses what is its charge, represented by a Roman numeral. So we'd have iron 2 or iron 3, gold 1 or gold 3, copper 1 or copper 2. So down here in these particular compounds, how do I know what the charge is on iron? Well, I can do an opposite crisscross when my subscripts are not the same. That means that iron was a +3, chlorine was a -1. I would say iron 3 chloride. Down here, subscripts are not the same. I pull up the 2, I pull up the 1. Iron was a +2, chlorine's a -1, iron 2 chloride. Now, when we have this example, when the subscripts are the same, it means they could have potentially been 1s, but they could have been 2s or 3s, because in a formula unit for an ionic compound, we always represent that as an empirical formula. So in order to find out the charge on copper, we have to know what is the charge on oxygen. I look at the periodic table and see oxygen is a group 6 nonmetal, which means that it takes a -2 charge. Since I only have 1 copper atom, that means that it has to balance out the charge on oxygen. Therefore, copper must be a +2. So I would say copper, parentheses, Roman numeral 2, oxide. Copper 2 oxide. So those are looking at binary compounds. And in a binary compound, you're always going to take an IDE ending. Now we have polyatomic ions, which are actually molecular compounds that have a charge to them. So they're covalently bonded, but the entire group holds a charge. Poly meaning more than 1 atom. So since they're still positively or negatively charged, they can form ionic bonds. So some examples would be the ammonium ion, which is the only polyatomic cation that we're interested in. And then sulfate, which is SO4 2-. We can still employ the crisscross method to form compounds with these particular substances as well. So here's a list, and there's a table in the book that tells you what some common polyatomic cations and anions are with their specific charges and their formulas. So how do we name these compounds? Well, I look at what's showing up in the front here. I notice I have NH4, which I just have to recognize is the ammonium ion. So I have ammonium, I have Cl, so that's chlorine. I change the ending, IDE, ammonium chloride. Here, if I split this down the middle and I go after the first element that I have a metal, barium. It is not a transition metal, so I don't say barium 2, I just say barium. And then I look to see, well, what is my SO4 called? Sulfate. So this compound is barium sulfate. I look and I see the first element I come to is iron. Iron is a transition metal, so it takes a special charge. I figure out what my charge is by looking at what is the subscript over here and doing the opposite crisscross. So iron is a +3. This is a special group called nitrate. So I would say iron, parentheses, Roman numeral 3, nitrate. Down here, copper, if I split this apart, I recognize this is a metal. It's a transition metal, so copper is a +1 or +2. How do I figure that out? Well, I can't do the opposite crisscross because I notice that this is an entire group. If I've split the metal away from what's left, I know that this is a group here because I have more than one atom. So this is called the bicarbonate ion or the hydrogen carbonate ion. It has a -1 charge. Since I only have one copper atom, that means that it has to be opposite in charge. So this would be called copper, parentheses, Roman numeral 1, bicarbonate. Last, we have a metal, calcium, which is separated from this polyatomic. Calcium is a group 2 metal, so it does not take a special charge because it's always a +2. So we don't say calcium 2, we just say calcium. The OH is a polyatomic, which has its own name called hydroxide. So this compound is called calcium hydroxide. So writing formulas from names of ionic compounds. We always have to make sure that we're determining the charge of each ion, and we write the formula so that the resulting compound is neutral. So for example, barium chloride, I know that Ba is a +2 because it's a group 2 metal. Chlorine is a -1 because it's a group 7 nonmetal. I do my crisscross and I end up with BaCl2. So determining formulas from names. Write the formula for the following ionic compounds. So I look to the periodic table, find sodium, see it's a group 1 metal, which means it's a +1 charge. This sulfate, this 8 ending tells me that this is a polyatomic, so I have to look at the table and see what is this compound. Sulfate is SO4 with a 2- charge. So sodium's a +1, sulfate's a -2. I do my crisscross and end up with Na2SO4. Ammonium sulfide. The IDE ending tells me that I just have one element. That element is sulfur. Ammonium is a compound, is a cation that's a polyatomic. So I have to look at the table. That's NH4 with a +1 charge. Sulfur is a group 6 nonmetal, so it takes a -2 charge. So when I need more than one of a particular group, I use parentheses, and it would be parentheses NH4 2 S. Magnesium phosphate. Magnesium is a group 2 metal, so I know it's a +2 charge. The ATE ending here says I'm something special. I'm a polyatomic that has a bunch of oxygens. So I look at my table and see that phosphate is PO4 with a 3- charge. I crisscross my 2 and my 3 and end up with Mg3 parentheses PO4 parentheses 2. So here I have a transition metal. I know that because it tells me this is what the charge is. This is chromium with a +2. Oxide, IDE ending, tells me this is just one element, and that element is oxygen. It's a group 6 nonmetal, so it's a -2. If I have chromium with a +2, oxygen with a -2, they cancel each other out, and this formula would be CrO. So that covers ionic compounds. So now how about covalent compounds? So these atoms have similar tendencies to gain or lose electrons. And really, we're looking at elements that really want to gain electrons. If I'm nitrogen, I want 3. If I'm fluorine, I want 1. So who's going to win that battle? So covalent compounds are called molecules because they exist as little discrete units. There are certain diatomic elements that have completely covalent bonds, which means that they are sharing their electrons evenly. Hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine all exist in nature as diatomic, so you never see one of these standing alone. So down here are some examples of covalent compounds. How do I know they're covalent? Because all the elements are nonmetals. If you see a metal, it's no longer covalent. So we have water, methane, ammonia, chlorine, and ethanol. How do we name covalent compounds? Well, the names of the elements are written in the order that they appear on the periodic table. Typically, an atom in a lower row will appear first in the compound. This is because it's bigger and can usually have more bonds around it. The prefix indicates the number of each kind of atom. So mono means 1, di is 2, tri is 3, tetra is 4, etc. There's a table here that tells you all of those up through 10. If the first element that we see is only one atom, then we don't say mono on the first one. The prefix for the suffix for the second atom is always IDE. So similar to when we looked at binary compounds for ionic bonds. And when we have oxygen and our prefix ends with an A or an O, we typically drop that so that we don't say tetraoxide, we just say tetroxide or monoxide as opposed to monooxide. So in practicing with these down here, I'm allowed to bond semimetals and nonmetals in covalent compounds. I'm just not allowed to bond metals. So Si happens to be a semimetal, but its name is silicon, not silicone. That's something completely different. So I have silicon. I have 2 oxygens, so I use the prefix di and say silicon dioxide. Over here, I have nitrogen, I have oxygen. 2 nitrogens tells me that I'm dinitrogen. 5 oxygens says I'm pentoxide. So not pentaoxide, we drop that A. So this name is dinitrogen pentoxide. I have carbon, I have chlorine. These compounds will always be binary. I name the carbon atom, it's carbon. I don't say monocarbon, I just say carbon. There are 4 chlorines, so that's tetra. I change the ending to IDE, carbon tetrachloride. Over here, I have iodine and fluorine. I have 1 iodine, so this is just iodine. I have 7 fluorines. I change the ending, and I look for my prefix for 7, which is hepta. So I say iodine heptafluoride. Now, going backwards from if I have a name and I want to find the formula, all I need to do is know what my prefix means. And that tells me the number of atoms. I'm no longer trying to balance anything based on charges because these compounds do not form based on charges. They form based on, I'm going to share so many electrons with you. So for example, nitrogen trichloride. N is nitrogen. Chloride is chlorine. There's 3 chlorines, so it would be NCl3. Diphosphorus pentoxide. Di means 2. Phosphorus is a capital letter P. Oxide means oxygen. pent means 5. So this would be P2O5. There are some common names that are used as opposed to saying dihydrogen monoxide or nitrogen trihydride. We call things water and ammonia, respectively. So practicing some more. Nitrogen monoxide. Nitrogen, there's just one because there's no prefix. Mono means one as well, so this would be NO. Tetraphosphorus decoxide. Tetra means 4, dec means 10, so this would be P4O10. So the last type of compound we're going to talk about how we name it are acids. So there's two different ways that we name acids, whether they're a binary compound or whether they have a polyatomic, which we would call oxyacids. Oxy meaning that they have oxygen associated. So if it's binary, that means you have hydrogen and one other nonmetal, period. The way to represent or the way to recognize whether something is an acid is to see whether there's an H that shows up first. If the H shows up first, that tells us we're an acid. We're not naming it as a molecular compound, and we're not naming it as an ionic compound. So we exclude oxygen and nitrogen because we know when hydrogen bonds with oxygen, we get water. And when hydrogen bonds with nitrogen, we get ammonia, which is actually a base. So for binary compounds, we say hydro in the front, and we change the ending of our other nonmetal to ic. And then we say acid at the end. When it's an oxyacid, now the polyatomic has a special ending. They have a special name. So if your polyatomic ends with ate, we change the ending to ic. If it ends with ite, we change the ending to us, and then we say acid. So the big difference between binary acids and oxyacids is that in an oxyacid, we never say hydro in the front. So for practice, HNO2. Well, I separate my H. I see that what comes after it is not just a single nonmetal. It's a compound. It's a polyatomic. It's an NO2. So I have to look at my table, see what that ending is. Nitrite. So I say nitrous acid. HCl, binary. I have H and only one other element. So I change the ending to ic, and I say hydrochloric acid. Here, I recognize that my H actually comes on the end. With organic acids, which is what this is called a carboxylic acid. Our H's are always attached to our O's. So whenever you see a COOH at the end, a COO, that tells you you're an acid. So if I separate my H here, I see that I have CH3COO, which is the acetate ion. Because it's a polyatomic, I change the ate to an ic and say acetic acid. So what happens if I have a name and I want to find the formula? Well, since I don't have hydro in the front, this tells me that I'm a polyatomic. My ic ending tells me that this was an ate before. So this was the phosphate ion. I look at my table and see that phosphate is PO43 minus. And then I form the compound by doing a crisscross. H is always a +1 when bonded with other nonmetals. So I need an equivalent number of H's as whatever my charge is. So this becomes H3PO4. Hydrofluoric acid, I have hydro in the front, which means that I have no oxygens. I don't have some polyatomic that includes oxygen. So I see fluoric, which came from fluorine. Fluorine is a -1. I put on the same number of hydrogens as my charge. So this is HF. Sulfurous acid, once again, I don't have hydro in the front. So this tells me that I'm a polyatomic. I'm an oxyacid. I have oxygens. I'm special. I have my own name. So if it was an us ending, that means that it came from being an ite. Sulfite. I look at the table. Sulfite is SO3, 2 minus. I put on an equivalent number of hydrogens. Since there's 2 minus, I need 2 H's to balance that out. So sulfurous acid is H2SO3. And the very last part of this chapter is looking at how can we find how much a compound weighs. So we talk about molecular mass, which we can interchange by saying molecular weight. So the molecular mass is looking at, for a compound that is covalent, how much do each of these atoms weigh? I'm going to add them up, and that tells me my weight. For an ionic compound, we call this a formula mass because we know in ionic compounds we have repeating units of positives and negatives. So we're just looking at that simplest formula, that empirical formula. But once again, all we're doing is I look at the periodic table, I find my element, I look at the mass, however many of those atoms I have, I add up all the masses, and that gives me my molecular mass. So in the compound SO2, which when I look at this, and since we're practicing naming, SO2 is a compound that is covalent. It is molecular because there's no metals. So that means I use prefixes. That's the only time I use prefixes, never with metals. So this is S for sulfur. I have 2 oxygens, so this would be called sulfur dioxide. So how do I know how much this weighs? Well, I look at the periodic table, and I see that sulfur is 32.07 atomic mass units. Oxygen is 16.00 atomic mass units. Because I have 2 of them, I multiply by 2, and then I simply add up my values to see that the mass of this compound is 64.07 atomic mass units. So atomic mass units are what we use to represent the mass of atoms. So it tells us in the name, atomic mass unit.